In this example, we're posed with a problem of having a magnesium alloy rod, which is encased in a brass tube. The left-hand side of the rod and the tube are welded to a rigid wall. The right ends of the tube and the rod are welded to this rigid connector there at B. Knowing the material properties for both the magnesium alloy and brass, the diameter of the rod, the outer diameter of the tube and the length and the axial load P, what we want to do is determine the normal stresses in each one of the two, the rod and the tube, and what is the elongation of this bimetallic rod. What I'm going to do is draw free body diagrams of the rod by itself and the tube by itself. So the rod, we're calling that element 1, so it's going to be carrying an axial load here of F1. The tube has an axial load there of F2. And so since both the rod and the tube are welded to that connector there at B, these two forces add together, F1 and F2. And then, of course, we have our applied force there of P. I'm going to use X to the right as this, so that whenever I write down my equilibrium equations, actually one of them, the equilibrium equation that I'm going to write down is going to be for the connector there at B. When I sum forces in X, if I just focus on B, I get minus F1 minus F2 plus the applied force P. So therefore, P is equal to the sum of F1 and F2. Not a surprise. But I'm going to call that equation 1. Then I'm going to write down the elongation equations. One for the rod, one for the tube. So for the rod, that elongation E1 is equal to F1 L1 divided by E1 A1. We can say that this is length L, so therefore from this I see that the load F1 is equal to the material property for 1, the cross-sectional area for 1, elongation of 1, divided by the length. So that's going to be my equation 2. And then for the tube, the elongation equation, very similar looking thing. So it's going to be F2L2 divided by E2A2. Again, the rod and the tube have the same length. So this gives us the F2 is equal to the Young's modulus for the brass, the cross-sectional area of the tube, the elongation for the tube, divided by L. So that is my third equation. So one thing I haven't said yet is something about the compatibility of these two elongations. And what I mean by this is that the elongation of 1 has to be the same thing as the elongation of 2. They're welded together on the left end, they're welded on the right end. So what I'm going to do is just call that symbol E. That's the answer we're looking for there in part B. So this is my equation 4. So in solving, what I will do is take and combines equation 1 through 4. 1 through 4 says that P is equal to F1, which is E1 A1 divided by L times E, plus E2 A2 over L. Again, that's all times E, the overall elongation. So actually, I'm going to be able to solve for answer B first. So B says that E, which is the elongation of the tube rod, the total overall, if if I just solve for that, it's the load P times the length L divided by the Young's modulus for the magnesium cross-sectional area for the rod plus E for the brass, A2 for the tube, and that's the overall elongation. Part A, we were asked to find the stresses in each. So sigma 1 is equal to F1 over A1. So that's going to be E1 A1 times E divided by A1L. The areas cancel out. So what I have here is the Young's modulus for the magnesium alloy divided by E1A1 plus E2A2, all times the applied load there for P. Sigma 2, that's F2 divided by A2. So that's equal to E2 A2E divided by A2L. A2s will cancel out, so we have a similar looking thing here of just E2 now on the top. So this is the numerical relationship that exists between the two. If we want to find the ratios of those, let's say sigma 2 divided by sigma 1, we can see that that's simply going to end up being E2 over E1. So the distribution of stress between those two goes strictly as the ratio of the Young's modulus of the two materials. So what did we do? First thing we did was write down an equilibrium equation for each one, both the rod and the tube. And then we looked at an equilibrium equation for the connector there for B. So that gave us equilibrium equation 1. We wrote down the elongation equations for both the rod and the tube. That connects elongation back to the load. And then the key part here was to recognize that the way the things are connected together, the rod and the tube have to stretch the same amount. So this gave us 4 equations. We solved for the total elongation. We solved for the stresses in both the rod and the tube individually.